I would like to present my project work that's retrofitting of the refrigerators for the demand response. I'm pretty sure that everybody, like most of you, actually seen some strange wires in the refrigerator in the guest room. That it's my project. So what is actually demand response? Demand response, that's a technique which based on the change of the usage of electricity of the end customers in response to the change of the price over the time. So what does this actually give us for the power operators? That provides new option to balance the demand and supply. So the network will be more stable and reliable. And additional reason that it can provide lower prices for the electricity, but unfortunately right now only for the industry scale customers, and maybe in the future also for the end use, like usual customers. So my project is how actually the domestic refrigerator can be extended for the demand response, what approaches can be used for that, and what results do they provide. So I started actually with the assessment of the normal mode of refrigerator, how it works. I assessed a few levels. This is the result of the level 3. That's this level 3 of the inner thermostat that provides temperature interval from 8.5 to 4.5 Celsius degrees. The red cycles, that's power consumption cycles, and the dashed blue line, that's average power consumption calculated based on every on-off cycle. So the average power consumption of the refrigerator in level 3 is 17.5 watts. This level was used as a base level for comparison with other approaches. So what approaches we actually implemented? The EPIX thermostat, that's an approach which changes the thermostat nominal temperature based on the power price from EPIX spot, and the frequency by thermostat, that's approach which adjusts load consumption based on the power availability derived from the frequency of the network. So in order to test this approaches, a testing environment was created that's based on the refrigerator. The additional temperature sensor was installed inside. The temperature receivers get the temperature from the temperature sensor. The power switch controls the power of the refrigerator and additionally measures the frequency and other parameters of the network. They both connected to the control computer, which runs the controlling programs, and it also has access to the internet in order to access the EPIX spots prices. That's basically the whole architecture. So the first approach can be described as this figure. So the base nominal temperature was set to 6.5 Celsius degrees, and the minimum price and maximum price in plus minus 12 hours range was projected to two values, 5.5 and 7.5 Celsius degrees. So the nominal temperature changes from 5.5 to 7.5 degrees, and the deviation gap of the thermostat, or other words, hysteresis, was plus minus 1 degree. So the final actually temperature interval will be 4.5, 8.5. That's the same interval which was chosen for the test purposes. So one of the results of such thermostat, the EPIX thermostat approach, is presented here. Here you can see the blue line, that's again the temperature. The broken green line, that's the nominal temperature which is changed over the time according to power prices. The red cycles, that's again consumed power, and the dashed blue line, that's average power calculated based on every on-off cycle. As you can see, the times when the price is low, so the nominal temperature is also low. That provides more power consumption consumed by the refrigerator, and the high price actually indicates the times when the refrigerator consumed less. Please ignore this step that was caused by sudden increase of the temperature. Probably somebody opened the fridge door like for too much time. So what actually these results say, that this approach can be characterized by the ability of the to increase or decrease the power consumption of the refrigerator. And for example, during high power availability times, that can be the power consumption can be increased up to 26%, and during a low power availability, or other words, high price, the power consumption can be reduced up to 14%. So the next approach which I represent, that's frequency aware thermostat. That's basically based on the normal thermostat, how refrigerator works. So there are two states, cooling state and warming state. They are changed when the temperature goes above or below the temperature borders. And in addition to that, two more states are added. When the frequency goes up from the normal value, from the warming state, the refrigerator can be turned on to the power excess state. That actually means that if the frequency goes up, we turn on the refrigerator to consume more power. And other way around, when the frequency goes below the threshold, we turn off the refrigerator to stop consuming the power. So these states are called demand response states, additional to the normal states, cooling and warming. So if the event time has expired but the frequency didn't go back, this state can be resetted, and then that consumes to stay in this state. Or if the time has expired and the frequency in normal state, so the demand response states will be ended and goes to the normal state. So demand response state, according to this diagram, demand response states can be activated only if the temperature of the fridge is inside of the normal temperature interval. When the temperature interval goes out, the system will be reset to the one of the normal states to make the temperature go back to the normal interval, because that's basically the user requirement. He wants to have the temperature inside of the normal interval.
But that was not modeled in your state diagram here.
Yeah, it is. You want the temperature below the mean border or temperature above?
Event time, and the event time expired.
For example, from the cooling state, we start the power shortage state. That can be, I will say about that later, that can be, for example, has duration up to 20 minutes. Then
or temperature above maximum. Okay, I didn't see the or. Yeah.
Okay, maybe I also.
That's it. Yeah.
I also didn't mention it.
Yeah.
So before implementing this approach, I conducted the calibration of the used devices. So the power switch which we used actually wasn't really accurate. The frequency measurement returned by the power switch was from 1.14 to 1.18 Hertz lower than real values. That's actually a big mistake, and that makes the device actually inappropriate for these experiments. But I will say in a minute how we overcome this inaccuracy. And
this was the device we bought.
Yeah. Additional calibration tests were conducted for the all-night thermometer. So that's also not very accurate. That provides 2 degrees Celsius greater value than real values.
That was the one inside the fridge.
Yeah. So the parameters of the frequency intervals, that's basically the borders which are used to indicate the power excess or power shortage states. So I implemented that not the fixed one, rather dependent on the temperature. With help of these factors, F shortage, F excess, They basically are calculating the current temperature according to the min and max interval and make refrigerators react to the power deviations differently. For example, refrigerators with different temperature will react differently. That helps to distribute the events between different refrigerators. That's very helpful in case of multiple refrigerator usage. So all the refrigerators will not react simultaneously, so they will not create new power imbalances. The duration of the demand response state is also dependent on the temperature. That makes additional dispersion of the demand response events. So in order to overcome the inaccuracy of power switch, instead of the nominal frequency value 50 Hertz, we used the average of the average value from 6-hour history. So this value was stable. At least this history value was stable. These constants, which are used for the calculating the frequency borders, were found by experiments and chosen this way that they provide not more than 4 or 5 demand response states or demand response events during the day. This amount was chosen just to make the analysis easy, just to have these events. I checked many parameters. For example, some of them actually was a sequence of uncontrolled demand response states. That basically means that too many states, or just those parameters which do not provide any demand response states at all. That means the frequency border are too big. So the durations parameters, minimum duration, maximum duration was chosen 15 and 30 minutes. So what does actually this result show? That's the results of one of the experiments. That's again the temperature, that's the frequency, and 2 borders. And for example, here with gray background, we see 1, 2, 3, 4, 5, 6 events. For example, this is the excess event when the frequency goes up and crosses the border. So refrigerator starts to consume energy, additional energy. This is again the excess event. This is again interesting point here. For example, that frequency, even the frequency event below the border, we didn't really react to this event because at that time refrigerator didn't consume any power. So if you don't consume, we cannot make it less. This is a shortage event. This is again the excess event. And this is a shortage. So this is the power consumption, the on-off cycles of power consumption, and the average power consumption calculated on the every on-off cycle. So how actually this approach can be characterized? This can be characterized by energy shifted in time, and the values for our experiments say that the amount of 12.524 watt-hours can be shifted in time. Also, the parameters that we chose provide, as I said, 4 or 5 events per day. But in the realistic case, if this system would be implemented in the industry, that's actually a very big amount. So that should be not, the occurrence of such events should be not bigger than 1 event per month. And in this case, the frequency should be close to the border 49.8 and 50.2. So the conclusions that are made after the project work that both approach can be used, successfully used for the demand response with a domestic refrigerator. This approach is actually hard to compare because they based on the different reactions to power availability, and the free prefix thermostat approach provides increase and decrease of power in these amounts, and frequency version thermostat power shifted in time can be power shifted in time can be from 12.5 to 24 watt-hours. That's actually it, but before that I would like to say that maybe somebody remembers at the beginning I promised if we have any failures I provide some ice cream. So to say the truth, we have one. So in the fridge there is some ice cream. You can have some. That's it actually. Thank you for your attention.
So why did you have for the two approaches so not the same criteria for evaluating them?
Sorry.
For the Apex thermostat, you have this percentage which reflects the change of power consumption. For the other approach, you have the power, the shifting. Yeah.
Yeah.
Why? Do you understand the question?
Yeah. Why are they different?
Yeah.
That's actually.
No. Why did you use different metrics?
That's actually like related to their reactions to the power availability. For example, if I go back to the Apex thermostat, as you can see, like the on-off cycles, they are mostly close to the normal behavior of the fridge, except only that they are starting to be more frequent and less frequent. So that can be characterized as ability to increase or decrease power consumption. And if you check the behavior of the fridge on the frequency aware thermostat, that's hardly to say that the power consumption is changed in the same manner. It's rather changed in the following manner. For example, here instead of the full on-off scale, we have only one part, and otherwise here instead of the full on cycle, we have two other ones which are divided by off cycle. So that basically means that the second thermostat approach, the second frequency aware thermostat approach, demand response approach, can be better characterized just with the amount of power which it can whether consume or like really consume more or just like leave out. That's why like that's difficult to compare them because they react differently.
Why does the power consumption decrease when the fridge is on? Yeah.
You mean why the blue line?
No. Why do you have this? I suppose these are the switch off and on points.
Yeah, that's.
So why is the power decreasing between these 2 points?
That's actually how the refrigerator works. As we like discussed with Dr. Rensky, I guess that's just because I don't know some oil or some other like mechanism are starting to work differently during the work. So like then, what is a refrigerator? Basically, it's motor and compressor. So maybe that's just works differently during the time.
Do you speak about the red line?
Yeah.
Going down? Yeah, that meant mechanical.
And here.
I mean, naively you would expect that it's constant.
Yeah. Even so, we also noticed that during every start of the refrigerator, the consumption peak can reach up to 1,000 watts. That's probably because of the starting current of the motor. That's just lasts after 3 seconds, but every start there is a very big peak.
Or is this a measurement error?
Could be, but I guess they have a capacity in it to compensate Blindleistung. Well, anyway, they have a capacitor in it, and if you switch it on, it charges, and that creates a peak. I guess that's something like that.
So, coming back to your conclusion, the power you shifted was 12.5 watt hours or what?
12.5 up to 24 watts.
So if you how many refrigerators are in Germany?
40 millions.
A bit more than that, yeah.
40 million. So how much would that be then, if all would use this?
600. A lot.
That was 20.
Ja. 8 Gigawatt?
Kann ich jetzt so rechnen? 40 Millionen?
24.
40 29 sind
800 bis
0,0
Megawatt.
nicht mal ein Gigawatt.
Wie viel ist es jetzt?
Weniger als eine Gigawattstunde.
Weniger als ein Gigawatt.
Stunde.
Stunde, ja, ist mir klar, ja. Okay. More questions? Yeah.
Generally, could both approaches be combined? Or have you tried? Or
No, we didn't try, but yeah, they can be combined. That like can be like the efficiency of like such method can be even like better. Yeah.
And my other question would go into the same direction. Have you estimated what potential there is? I mean, as I see it, you also have a quite short window of time where you can actually do something. So if there's a continued power shortage, then the cycle of the fridge in the end.
Yeah, like the maximum, like why we have this values actually like 12.5 and 24 watts hour. That's actually the length of the power consumption, which is can be consumed during this length, 15 and 30 minutes. Like 15 minutes was chosen as the maximum time during which that's basically related to power reserve technique. And this was taken as just double time of that. So if we change these parameters, of course we can achieve more shifted power. But from the other hand, like this amount won't be bigger than the whole cycle power amount. I mean, like we cannot shift more than the fridge consumes during one cycle. That's basically like this value is 50 watts multiplied by length of the cycle. That's
2 hours.
not 2 hours. That's only on site. Like, that's basically I have some additional slides. That's basically for the level 3 that will be 50.3 minutes multiplied by in average 50 watts.
Have you tried to calculate the virtual costs of your approach? I mean, you could have multiplied your power consumption with the stock price.
Yeah, like we have this idea, but I didn't really calculate that. So the answer is no, I didn't try, but like we discussed it.
Yeah, but this will only be a virtual price because we don't pay the stock.
Of course, but I mean, it would be also a price for the whole community.
Yeah,
if everyone has this this
society, you mean, yeah.
then there would be for the whole community average bound.
For the frequency approach, you don't need the EPEX exchange price. You need the one exchange price you just found out for load shedding. That was like, well, you found a pretty big price. But
Yes,
I'm not very sure if this is
400 euros per megawatt hour.
Well, I don't think that they will understand this. So currently, you're given money if you how do you say shed load after
load shedding.
Yeah.
That's okay.
But this is only for big industries. But you could have used this amount of money to evaluate that, yeah, which you did not do, yeah. Okay, yeah.
And did you analyze the power efficiency after implementing the changes? So I mean, how the total power consumption over a day is in relation to the total average temperature in a day. So you changed the behavior of the fridge, right? So maybe it's a little bit colder on average now, but you use less power or more power, or how did the efficiency change?
I would say that didn't really change a lot because I mean even if in the thermostat, as you can see, like the average temperature was still the same. Like so, there were times when it consumed more than the same, less, and the average power consumption of the fridge also stayed more or less like the same, 17.5.
So the question, if I interpret correctly, is if I would use it as a normal user, would I have spent more money or save money?
If you pay the same price, no, like that's the same price for the every hour. So I would say no, because the power consumption still will be like more or less the same.
They didn't change the power consumption, yeah.
I mean, like average,
yeah.
But
Well,
during different
Yeah,
hours.
if you would have to pay that, so this was not changed, because in the water bill it was changed, yeah?
Yeah, but the approach was pretty much different.
I know that,
So
so,
for the similar approach, A&T, it was not changed neither. So I had a similar approach to that. And it was
okay, so currently if you would install that, we would not pay more and we wouldn't pay less. So there's only some benefit for the, yeah.
In case if you pay different prices for different.
No, I mean, there's only a benefit in the sense of demand response that
Yeah.
the society, maybe we could switch off some reserve power stations, which we otherwise would have to have, yeah. Yeah,
How did you choose the threshold temperatures, the 8.5 and?
yeah, that would have been my
Are
question.
these the actual maximum values of the classical control unit from the fridge? Or?
Yeah. This like as I said, my beginning of the experience was starting with assessment of the normal,
Okay.
one. So this was the level 3 of the inner thermostat of the refrigerator.
Okay.
I set it as a level 3, and that's actually showed that the upper temperature is more or less stable, and it was 8.5, and the lower 4.5, and the power consumption is also periodic, and this period is stable, like more or less stable.
And if you use a different level, then these values change, or is
Yeah.
it just faster?
I have some for the different levels, for the 2 to 3, 3.5. The temperature range change, the average temperature also change, and the on-off phases also change. For example, I'm interested to notice that for the level 4, the refrigerator works even more time than it warms up.
And this is with the 2-degree offset, or is this corrected now?
This is actually what I've said you
The
mean.
2-degree offset.
You had some measurement error of 2 degrees.
They were already corrected after
is
the
corrected.
configuration, so this is actually the real values.
But then your diagrams were not corrected, correct?
No, because we like for the thermometer we actually used the data we actually achieved and like received this thermostat, so we didn't correct them. But like this is just I updated them just to show the final result of the modes, refrigerator modes.
So,
But may I quickly add that temperature accuracy is a problem anyway. If you go to the next backup slide, there you see that we have 50 degrees difference between the warmth and the coldest point. So 2 degrees measurement error is,
inside the fridge.
yeah. I guess when it was the cooling was on, right? That's the reason, because for the minus 40 degrees.
I mean, like anyway, the evaporator of the refrigerator is located in the back wall, so that's pretty cold anyway. So up to minus 40.
Well, this is the sort of the back wall.
Yeah. That's where evaporator is located. And for example, just the lamp, which can work during the door opening, so it's to the. I can give only advices that, for example, if you want some cool, like not very cold, so you can probably put your stuff in the refrigerator door, because that will be the most warm place in the fridge.
And if you wanted to have real cool, you should
just
be in
close.
contact with the back wall.
The ice cream.
Exactly.
So where's the ice
Did you push the ice cream to the back?
No, I didn't.
Oh.
So, coming back to this other slide with the levels. So you've chosen the measurement based on level 3. So my question is, how sensitive is your approach to these boundaries? Do you understand the question?
Yeah, I understand. I didn't check that. That's like didn't have actually time for that, but that was mentioned in my discussion part that additional work can be actually implemented with different levels, not just one, because we like assessed only one, and the further work can.
So what would you expect if you've chosen, for example, level 4? Level 4, geht es unter 0 dann? Wow.
Stellen Sie nicht auf die maximale Stufe übers Wochenende. Das ist gut.
No.
I understood.
Now, you see, if I'm correct, the difference between max and low is almost, it's almost always 3, isn't it?
No,
Wow.
not always. That's actually hard to say. That's which.
Das wird mehr, wenn Sie je kälter Sie stehen.
All right. Okay. So anyway, what would you guess what would happen if we have chosen the value according to level 4 or level 2? Yeah. Would the load you shifted, for example, in the frequency approach, have changed? Would it be more than 12 and a half or less? Do you understand the question?
Yeah. In frequency approach, that's one probably change a lot. I mean, the
That
time,
will not.
the amounts of the shifted energy in the frequency approach is more specified by the duration of event stance that event demand response event that we have, duration of it. But in case of the apex thermostat, when we actually update the nominal temperature, that probably can have some changes because the lower temperature are in the refrigerator. So the temperature resistance of the refrigerator, like the refrigerator, behaves differently. So I mean, like when the more cold the refrigerator lose the cold more quickly.
Mm-hmm.
So that actually can bring changes in the approach.
Okay. So how long did you run your experiment?
A long time, like in order to.
No, not for this. The other
Frequency.
Yeah, for example.
Like with every parameter, I set more than 20 different parameters in order to find out this exactly constants that we need. I ran more than 20, and every one of them was lasting around 3-4 days. From 3 to 4 days.
And on these figures, can you see when someone opened the fridge?
Yes. For example, I even can show that. I would definitely say that was open in the fridge because the power consumption was increased by 15 watts of the lamp.
Mm-hmm.
And the temperature like didn't go smooth, but like with some like step.
So switching off the lamp, would that change something considerably?
Not much, because that's just a few seconds, and the amount is not very big. I mean, like more problem will bring just frequently opening, because the air inside of the refrigerator is changed with the temperature, with the air from the room, and it's much more bigger than the environment of the refrigerator. So that will make the refrigerator work more.
Okay, and weitere Fragen mehr?